Let's say you ask an AI agent to process your Q4 expense receipts. It opens the finance apps, starts clicking around, and then it freezes. It throws an error screen. The agent understands what an expense report is, but it doesn't know your company's specific validation logic. This is the core tension of modern AI. General-purpose large language models possess immense reasoning capabilities and broad knowledge, but they lack specialized, step-by-step procedural expertise. You might think retrieval-augmented generation, or RAG, solves this, but RAG only retrieves passive text. Handing an agent a PDF of a corporate policy doesn't give it a multi-step executable workflow. Traditional tool use or function calling also falls short. Tools execute atomic, isolated tasks, like converting a file or pulling a single database entry. They do not teach the agent how to string those isolated tasks together to solve a complex problem. And fine-tuning an entire model for every specific corporate workflow is prohibitively expensive and far too rigid for real-world enterprise environments. To achieve actual autonomy, agents require a mechanism to dynamically load specialized workflows exactly when they need them without overwhelming their context windows. In late 2025, the AI industry converged on a standardized method for packaging this knowledge: agent skills. An agent skill is a self-contained file system-based package. It bundles natural language instructions, executable scripts, and reference documents into a single directory, all organized around a standardized instruction file called SKILL.md. While a traditional tool simply executes a command and returns a result, a skill alters the agent's pre-execution context. It injects procedural intelligence, preparing the agent's logic and setting its system permissions before it takes any action. We are going to examine how this architecture operates, how it directs agents to control graphical computer interfaces, and why its current design introduces a severe security vulnerability. Adopting these skills allows AI agents to follow complex, multi-step standard operating procedures, rather than executing single, disconnected commands. This architecture relies on progressive disclosure. Without it, loading hundreds of procedures would exhaust an agent's context window. Level 1, the metadata layer, loads only a tiny YAML front matter, about 30 tokens, acting as a lightweight routing table. When queried, Level 2 injects up to 2,000 tokens of specific workflow instructions into the context window. Finally, Level 3 dynamically loads unbounded external assets, like Python scripts or PDFs, only when required. Progressive disclosure structures information exactly like an employee onboarding guide. The agent reads the table of contents first, then pulls dense technical appendices only when tasks require them. The Model Context Protocol, or MCP, matured into an open standard providing the universal connectivity layer. It standardizes how an agent connects to external environments, like databases. Agent skills operate orthogonally, providing procedural intelligence. They dictate what the agent does with that data. A skill might instruct the agent to query an MCP server, format outputs, or run fallback scripts. Neither standard replaces the other. Together, agent skills and MCP form the decoupled architectural stack required to build reliable, production-grade digital workers. The ultimate stress test is the computer use agent. Operating a graphical interface inherently requires deep sequential procedural knowledge. This diagram maps a skill-equipped CUA finalizing expense reports. The skill router extracts the procedural package and injects instructions into working memory. This enriched context guides the agent to perceive the screen, ground UI elements, reason, and act. Integrating skills into this perception action loop allowed frameworks like OpenQA to achieve success rates matching human baselines on strict operating system benchmarks. By isolating how-to knowledge into external skills, the language model doesn't have to memorize workflows. Instead, it dedicates its processing power entirely to visual grounding and real-time reasoning. But this file system-based architecture has a severe design flaw. It relies entirely on implicit trust. In early 2026, researchers analyzed over 42,000 community-contributed skills across major marketplaces. They discovered that exactly 26.1% of these skills contain critical security vulnerabilities. This happens because agents treat Level 2 instructions as authoritative context. Attackers can easily embed hidden prompt injections inside long SKILL.md files, and the agent executes them without question. One documented attack is the context override. A benign skill exploits a "don't ask again" user approval, carrying that approval over to silently escalate its own privileges for subsequent malicious actions before the user notices. The most dangerous vector involves Level 3 bundled executable scripts. Skills containing executable code are 2.12 times more likely to contain vulnerabilities than instruction-only skills. Security analysts identified two primary attack archetypes in the wild. Data thieves exfiltrate credentials via supply chains, and agent hijackers subvert decision-making logic to perform unauthorized actions. Because agents treat these files as authoritative context, the current model of implicit trust is unsustainable. Securing the system requires a verification process that audits a skill's intent before it reaches the context window. To survive this threat landscape, the agentic ecosystem must abandon binary guesses about whether a file is safe or unsafe. It requires a formal, capability-based governance framework. This is the proposed Skill Trust and Lifecycle Governance Framework. It is designed to map a skill's acquisition provenance directly to strict deployment permissions. It begins with defense and depth verification gates. Gate 1 applies static analysis and dependency scanning to catch known vulnerabilities. Gate 2 utilizes an LLM-based semantic classification to detect intent mismatches, identifying those hidden prompt injections. Gate 3 deploys a behavioral sandbox to track invisible side effects during execution. Finally, Gate 4 validates a formal permission manifest, comparing declared tool requirements against the actual behavior observed in the sandbox. Surviving these specific gates determines a skill's trust tier, enforcing the principle of least privilege. Unvetted Tier 1 community skills are entirely sandboxed. They are granted zero tool access. Only vendor-certified Tier 4 skills that clear all verification gates are granted dangerous Level 3 code execution capabilities. This framework directly aligns the progressive disclosure architecture with progressive security permissions, effectively neutralizing the threat of malicious script bundling. Agent skills function as an abstraction layer that allows general-purpose models to load specialized external expertise on demand. However, the ecosystem remains in a vulnerable pre-governance phase. The security pipelines and verification standards built over the coming months will dictate whether this technology securely scales across the enterprise or collapses under its own exploitability. By mastering both the architecture and strict governance of these skills, we move away from querying monolithic AI oracles. Instead, we enter an era of modular, secure, and highly deployable digital workers.